I will begin today with a little bit of a digression. This is a suggestion from Simon to show you how semi-direct products of groups are very easy to think of. Suppose you have a representation of a group G on a vector space V. So this is a digression, and I will return to yesterday's topic in a little while. And I thought I'll mix in some history, interesting snippets in this connection. Now, of course, G is a group, and you have seen that vector space can also be thought of. Is that all right to have these lights on? You can, huh? Yeah, okay. You know, as an example, we said that a linear vector space is an abelian group, and the group operation is addition of vectors. So now, here is a very nice construction. We can make a semi-direct product out of the group G and the vector space on which you have constructed its representation. Here is how we do it. We invent a group with elements made up of pairs of this kind, G, little g from the group capital G. X is a vector in the vector space V. And now let us just declare that the group composition law in this new object is the following. Now I leave it as an exercise for you to check that this is a perfectly acceptable group composition law. You can see that the elements of capital G just compose by themselves. What about the elements of the vector space V thought of in this context as a group? They don't just mind their own business. The composition law for that part of this composite object is that you add x prime not to x but to the result of acting on x with the element G prime. This is this automorphism part which I had talked about. And remember, the vector space when thought of as a group is an abelian group. So any non-trivial automorphism on that will have to be an outer automorphism because it is itself abelian. So from a representation of a given group on some vector space, we can create this semi-direct product group. Is this what you had in mind? So very neat, cheap, but now I will show you why it is not so cheap. And this is a little bit of interesting history. It is ancient stuff, but I think money will appreciate it, and I hope some of you will also appreciate it. I am using up some amount of time on this. Now you know that in quantum mechanics, when you do perturbation theory and so on, there is an approximation called the Born approximation, and that is used, I think, mainly in scattering theory. And the Born approximation is used. Now this looks like a long story, so first let me mention I checked with Simon. Suppose the material I hope to cover cannot be covered in 40 lectures. What do you say? He said, don't cut down on the material, we'll have more lectures. So then it has made things a little easier for me mentally. I don't worry about how long the whole thing will take. So with that spirit, I am indulging in a little bit of diversion here. Now, in the Born approximation in quantum mechanics is applied when you can think of the potential energy in a non-relativistic quantum mechanical problem as weak or as a small perturbation. So kinetic energy dominates the potential energy, and then you have the Born approximation Born series and so on. Now, very interestingly, there is another regime called the strong coupling regime, where you imagine that the kinetic energy is very small compared to the potential energy. So you treat the kinetic energy as a small perturbation, potential energy as the dominant part of the Hamiltonian. This is not easy to imagine from a physical point of view. It really requires some amount of effort to understand what is going on. Quite interestingly, this strong coupling idea was studied very seriously in the maybe late 1930s, early 1940s. And it was particularly studied in the 40s for the system of pions and nucleons. Early 1940s, there were quite a few papers on this subject. So let me just say, from 40s up to 60s, there was a fair amount of work in applying this strong coupling idea to elementary particle physics of those days, when strong interaction physics, when nucleons, neutron and proton, and the 3 pi mesons were the main particles which were being studied. Some of the important papers in this subject I should mention to you. There is a physical review paper by Pauli and Dankoff, which was written around 1945. It is a classic paper. It's so beautifully written, such an education to read it. I went through it in great detail at one time. Then, I hope you are all familiar with this name, S.I. Tomonaga. He wrote a series of papers in Progress in Theoretical Physics, the Japanese journal, on this subject, roughly in the same period, 40s, maybe 50s, I don't remember. They are also very beautifully written. And I'm making some comments because there are fresh students here, and these are things which they might not otherwise hear. I want to mention about Tomonaga, his writings are extremely beautiful, extremely lucid. And there are 2 books, textbooks of quantum mechanics by Tomonaga, and I'm sure the Math Science Library has them. Please, you are young, you can stay awake for many hours in 24 hours, not like me, not like us. So please make the effort to have a look at Tomonaga's books on quantum mechanics. See how beautifully they are written. Tomonaga spent a few years with Heisenberg in Leipzig in the 1930s, and then went back to Japan, and he was influenced by the new quantum mechanics directly from Heisenberg. He has also written a very beautiful book called The Story of Spin. I don't know how many of you are familiar or know about this book. It was published roughly 10 years ago. It was based on lectures which he had given at in Japan, maybe at Tokyo University, I don't know. So one or two of his younger colleagues put together all the lecture notes, and this has been published by Chicago University Press. As I say, it's about 10 years ago, and once again, it is a beautiful book, very nicely written, with so many historical facts. And one of the things very nicely described in that book is this discovery of the Thomas precession. Very, very beautifully done. And then how Dirac discovered the Dirac equation. Very nice book. So I'm mentioning it to you. Coming back to strong coupling, see, I have to relate it to this, and I will. The other important person who did initially very good work on strong coupling theory was Gregor Wentzel. And that is relevant to this institute, as we will tell in a little while. Wenzel is the same Wenzel of the WKB approximation. Do you know what WKB is? You all know. The semi-classical approximation in quantum mechanics. You know the names W, K and B. W is Wenzel. Brillouin. There's a fourth name also, Jeffries. So it's called JWKB. So this is that Wenzel. Now, from the work of Pauli and Dankoff in this context, a prediction of their work in strong coupling theory for the system of pions and nucleons was that there should be a excited state of the nucleon with the spin equal to 3/2 and isospin equal to 3/2. I'm not going to explain isospin, but many of you may know it. And this was a prediction, and many other particles were also predicted. And indeed, a few years later, Fermi discovered what is called the 3-3 resonance. Isn't that right? In 50s or something like that, or late 40s? 50s, early 50s. So Fermi, the experimentalist version, he did in the pion nucleon scattering experiments, he showed there is a resonance state of this kind. So you can say it was a prediction of strong coupling theory, and it was experimentally found. Then in the 1960s, there came a very, very beautiful paper. It is by 3 people, Cook, Gable and Sakita, in which they showed that the essence of strong coupling theory could be expressed in the language of Lie groups. And the title of their paper was called Lie group of the strong coupling theory. That was the name of their paper. And what did they find? They found that in this strong coupling limit, a system like this, or any generalization, if set of baryons plus mesons interacting with each other in the strong coupling limit develops a special symmetry, and that symmetry group is a semidirect product exactly of this kind. It is a part which is the original symmetry, for example, isotopic spin, and then an abelian part. And this so it's a very beautiful paper. It's called the Lie group of the strong coupling theory. And so from their work, the result, what Pauli and Dankoff had found, for example, could be read off much more easily. It was very, very influential, very highly quoted work at that time. So it was their achievement to show that this kind of semidirect product is physically very important in such theories. Now, this paper was referred to by everybody as the CGS paper, Cook, Gable and Sakita. Around that time, I think that was in 64 or 63 or 65, something like that. That is when their paper came. Around that time, one Jacob Kurian, who is originally from Chennai, I don't know if at one time he was a student here, I don't know, in the early 60s, he and I were both working with the ECG Sudarshan. And we wrote a paper on this subject, and we called the MKS paper. So both CGS and MKS versions are there in this, and we also try to use this kind of mathematics. Simon will remember, it is exactly the work of Cook, Gable and Sakita that you and I and Subhash, we used for solving the problem of Wigner distributions for Lie groups. So you see how different things can get connected, can get exploited from one place to another. The last thing I want to mention in this digression is the connection of Wenzel to this institute. Professor R. Ramachandran, the previous director, was a student of PhD student of Wenzel in Chicago in that period, 1960s. His thesis work was on strong coupling theory. But I don't know if he used this group theory technique or more conventional quantum field theory technique. I think it was conventional particle physics. But his not exactly, no. I think the idea was to have a paper which could be referred to in this way. Not an important paper, but that was the idea. So anyway, so Wenzel was I don't know. So Wenzel was Ramachandran's guide. Ramachandran's thesis work was on strong coupling theory. This much I remember very well. So you can see this kind of semi-direct. So it is very nice that Simon told me yesterday evening that given any linear representation of any group on some vector space, you can immediately put it into the semi-direct product structure. And then it reminded me of this. So it is very nice to be able to view it in this way. So it shows that semi-direct product occurs very naturally. Okay. You want
space-time groups could be of this.
Yeah, Euclidean group, Poincare group, Galilei group also. So anything, so this is the end of the story. Now, you want to add anything? Not enough. So now we go back to what we were doing yesterday. We were talking about a representation being reducible or irreducible, and in the case it is reducible whether it is decomposable or indecomposable and so on. So supposing you have the case of a representation which is reducible and also further it is decomposable, then what it means is that the original representation space can be expressed as a direct sum of two subspaces, and the representation D acting on V also splits up into a smaller representation D1 acting on V1, D2 acting on V2, and D itself is a direct sum of D1 and D2. If this happens, then you can say, now let us examine the representation D1 acting on V1. Is it reducible or is it irreducible? And D2 on V2, which kind is it? And we can go on repeating this analysis. If the original representation is a unitary representation, then we can see without any difficulty, reducible means automatically decomposable. Why? Some of you had already guessed yesterday, in the case of a unitary representation, it means the vector space has a nice Hermitian scalar product. Then, and only then, the concept of the orthogonal complement is defined. And if V1 is known to be an invariant subspace, we just take V2 to be orthogonal complement of V1, and then you can easily convince yourself if V1 is preserved by the action of the group, and if the action of the group is unitary, that action will preserve V2 also. So given a V1 which is invariant, you can always find a V2 to accompany it to continue the reduction to achieve a decomposition. So for unitary representations of any group, this will always be decomposable. You will not come across indecomposable representations. It's also true that for simple groups, finite dimensional representations, they are fully decomposable. All finite groups, all finite groups, every representation is equivalent to unitary, so you will never have this indecomposability problem. Compact groups, no problem. Non-compact groups, like the Lorentz group, because it is simple, in the sense I said there are no invariant subgroups, it turns out every representation is again fully reducible. Okay. So the indecomposable cases are somewhat rare, but I showed you yesterday, I mentioned yesterday, a very interesting physically relevant case which Matthew's student Simon had studied long ago. So assuming we have a unitary representation, you can keep carrying out this reduction again and again until you hit rock bottom. And what will you find at the end of this repeated reduction? You will find that you have arrived at unitary irreducible representations where it cannot be carried any further. So it means that for the groups that we shall be concerned with for most of the time, compact groups and certainly all finite groups, you can say that these are the basic building blocks of unitary irreducible representations of groups are the basic building blocks of representation theory. It is true for finite groups, it is true for all compact groups. It is not true for non-compact groups in general. Okay, so this gives you an idea. It is important for most purposes to find out all the possible unitary irreducible representations of a group. Now, for this purpose, there is a very famous, elegant, powerful lemma called the Schur Lemma. Schur is the name I had mentioned yesterday, so I will now describe the lemma and prove it because it is quite elementary, but it's surprising in its consequences. A very nice lemma. So we will look at the proof of the Schur lemma and couple of applications. I hope I will be able to do 2 of them today. So it's a very powerful tool to analyze irreducible representations, find out when they are equivalent to one another, when they are not equivalent to one another, and so on. So we have a group given, we have a representation D on V, we have some other representation or maybe the same one, D prime on V prime, and assume be irreducible. Both are irreps. And let us assume for simplicity that these are all complex vector spaces. Supposing somebody is able to construct a linear transformation T mapping V to V prime such that this equation is true for all group elements. Suppose you are able to construct such a T, or suppose somebody else is able to construct such a linear operator T, going from the space of the first representation to the space of the second representation, obeying this equation for all group elements. We say that this T intertwines the two representations. That is the word used. That is how this relation is described. There is an intertwining operator between D and D prime. Then we can prove the following, and this is Schur's lemma. Case 1, D prime and D are not equivalent, and moreover T is identically 0, or T is non-singular, D prime and D are equivalent. This is the statement of the Schur lemma. Only these two possibilities arise. Now you might wonder, you have to look at the writing very, very carefully, and you might wonder, what possibility is forbidden by this lemma? Isn't every possibility appearing in either 1 or 2? I want you to be very, very careful here. Let me just help you. For a general linear transformation T from one vector space to the other, one possibility is T is 0. That's a trivial case. If T is 0, sure, this equation is satisfied, both sides are 0, you cannot draw any conclusion on any relationship between D and D prime. What is the other possibility? T is not 0. Then you might get something useful from this statement, from this intertwining relationship. In case T is non-zero, it splits into two possibilities. One, T may be non-zero, but it may be singular, which means what? It does not have an inverse. The other possibility is that it is non-zero and it also has an inverse. So these are the situations that can arise. So first tell me, is there any other possibility that I should list? Or is that a exhaustive listing of all possibilities? Huh? Pardon? Yeah, in which case does it not fall in one of those? I mean, that is, if V prime equals V, then it might be T equal to identity. Is that not covered in that list? It is exhaustive, correct. All right. Now, I won't tell you the answer. This is, I say, the statement of the Schur lemma. It says either this should happen or that should happen. Look at this statement very carefully. Statement of the lemma. We are going to prove it in a little while. Compare it with that complete list of all possible situations that can ever arise. Tell me, what conclusion can you draw? What does this lemma say in terms of that exhaustive list of possibilities?
Tells nothing about that singular case.
Huh? Tells nothing or tells something? Think very carefully, it's a subtle point.
Singular dimension was V and V prime will be different.
Beg your pardon?
V and V prime dimensions will be different.
In which case?
If T is singular.
If E is singular,
Yeah, let me hear all possible opinions, and then I'll tell you.
if D is singular, D and D prime are inequivalent.
Because the dimension
If T is singular,
D and D prime are inequivalent.
any other opinion? First, let us make it clear. We can disregard this case. if t were actually 0, you can't draw any conclusion on a relationship between d and d prime. Does this theorem, does this lemma, I am leading you to the answer. Huh?
T singular does not arise.
T non-zero and singular
Does not arise.
does not arise. Wonderful. You have caught it. It says, the Schur lemma says, this can never happen. Do you see that? Why don't you explain to others if they have not seen it, why the lemma says this is disallowed?
Because either d prime and d are equivalent or inequivalent. If they are inequivalent, then t is 0. If they are equivalent, t is non-singular.
Provided it is non-zero,
Yeah, non-singular.
it is non-singular.
Yes.
If a non-zero t exists, it is so non-zero, it is even non-singular. You understand what I mean? A matrix may be non-zero, but it may be singular. It may not have an inverse. Even though it has some non-zero matrix elements, determinant may be 0, then it has no inverse. Schur lemma says that cannot happen. So I'm very glad you spotted that the lemma is non-trivial. It is not that everything under the sun is allowed. It says this case can never arise. All right. So if anybody is not completely clear about it, during the tea break, you can ask, what's your name?
Sivateja.
Huh?
Sivateja.
Sivateja. From?
IT Madras.
You have to ask Sivateja in the tea break if the thing is not clear to you. Now let us actually prove this Schur lemma. Proof. It's so simple and so nice. I will define what is called the null space of T, which means what? The set of all vectors in V which are annihilated by T, that is, which are mapped into 0 by T. And this is therefore a subspace of V. I have said it in words. The null space is the set of all vectors in V such that when T is applied to them, the answer is 0. So that is clearly it's a subspace because linear combinations of such vectors also will lie in the same set. Okay? So this is a subspace of V. And the range of T is the set of all vectors in V prime which you get by applying T to all possible vectors in V. So what can you say about the range of T? Where does it lie? Is it a subspace of something? So subspace in V prime. Okay, so these two, given a linear transformation T from one vector space to another, its null space and its range are obvious and immediate definitions. Now, let us exploit this intertwining relationship. Suppose you take vectors in the null space and apply both sides of the equation 42, the intertwining relation, to vectors in the null space. So shall I write it now? Suppose x is in the null space of T, because x is therefore a vector in V and it is annihilated by T. Apply both sides of this to x. What will you get on the left hand side? Please dictate to me. What is on the left hand side?
T operating on dx. It shows that d takes a vector from one space to another.
Yeah, just one moment. Let's do it step by step. What do you get on the left hand side? This is what you get on the left hand side. I have not done anything, just written x on the right hand side. What do you get? Sorry, this is on the left. What do you get on the right? 0. So what do you conclude? T acting on this is 0. So what does it mean? Belongs to the null space. right? What does it mean? If a vector is taken from the null space and the group is allowed to act on it, you remain in the null space. So the null space is a subspace of V invariant under the group action. In the same way, I leave it to you to convince yourself the range is also a subspace of V prime invariant under the group action D prime. The null space is invariant under action by D of G. The range is invariant under action by D prime of G. One is in V, the other is in V prime. Now we use this statement. Both of these are irreducible representations. Okay, it's by assumption. D and D prime are both irreducible. What does that mean? What can the null space possibly be if one knows that the representation of V is irreducible? It cannot be a non-trivial subspace. So either it is the whole space or 0. Suppose it is the whole space. What would it mean? T acting on everything is 0, which means T is 0. We don't want to deal with that case. So the null space must be 0. 0. That's the only possibility. Because D of G is irreducible and we assume T is non-zero. If T is 0, we can go right away for T. Right? So I am assuming it's not a trivial situation. If this is true, what does it mean? It means that the operator T does not annihilate any non-zero vector. It means that it is one-to-one. Distinct vectors in V are mapped by T into distinct vectors in V prime. Okay, that part is clear. Then you look at the range part. And we use the fact that given information that D prime is an irreducible representation. So what can the range be? It cannot be a non-trivial subspace of V prime. Either it is 0 or it is the full space. If it was 0, what would it mean? Again, T is 0. Avoid that. So what is the range equal to? V prime. So the mapping T is one-to-one because this is 0 onto because of this. So what does it mean? It has an inverse. So we have proved this lemma. It is so elegant, so simple, but as you will see, it's very, very useful, very powerful. So do you all agree that we have proved that these are the only two situations that can arise if one has an operator intertwining two irreducible representations? These are the two situations that can arise, and as Shivateja pointed out, this in principle possible situation cannot arise for irreducible group representations. Okay, so now I rub this out. So having proved this Schur lemma, we will now look at applications of it.
Maybe I should add explicitly that
Yeah.
the proof that we have indicated,
Yeah.
the fact that, that T can, the two can be of different dimensions gets proved out.
Huh?
That the two spaces can be of different dimensions gets proved out.
If they are of different dimensions, the only option is T equals 0, which is always possible. So if they are both irreducible representations and they are of different dimension, there can be no non-zero T intertwining them. That is correct. Quite right. Yeah. So now we are going to look at actually three very useful applications of this lemma. So I want to be sure you have understood the lemma and see how elegant the proof is, how simple, but the idea is so nice. So now let's look at application. You will notice that I am avoiding writing things low. Again, there is a reason which Mani will sympathize with me. They say that you are getting old if when you bend down to tie your shoelaces, after you have tied your shoelaces, you say, is there any other job I can finish before I stand up while I'm still down? So you try to minimize the number of times you bend down. So now, first application. Suppose we assume we have a single irreducible representation. The two vector spaces are the same and the D's are the same, and we apply the Schur lemma to that case. Certainly the lemma did not say this is not allowed. So what we are given is some operator T which commutes with all the operators, all the transformations of some irreducible representation. Of course, T may be 0, then there is nothing to say. But if this is true, take any scalar lambda, multiply it by the unit matrix or unit operator, identity operator in that vector space. This is also true. All right? Okay. Choose lambda so that it is an eigenvalue of T. It's a root of the characteristic equation for T. It will mean that this has a 0 determinant. If it has a 0 determinant, it is singular. If it is singular, it cannot be non-zero. Schur's lemma. So you see, it's like a pincer movement. You choose lambda so that this has a vanishing determinant. Therefore, it is singular. The only way a singular matrix can commute, singular operator can intertwine two representations is by actually being identically 0. Not non-zero and singular, but 0 and singular. So what do you conclude? An operator which commutes with all the operators of an irreducible representation can only be a multiple of the identity. It's a very simple, very nice result. So this was, I don't remember some equation number, doesn't matter. So it can be proved if a non-trivial operator, a non-trivial meaning not multiple of identity, if a non-trivial operator commutes with a given group representation, that representation must be reducible. That statement you can make. Conversely, a representation is irreducible if and only if only multiples of identity commute with it. So all these statements, they are, same content. Okay. So this is the first application of the Schur lemma. It talks about a single irreducible representation and tells you only trivial things can commute with a set of operators giving an irreducible representation of a group. The next application is really quite subtle, and I would like to go through it. carefully with you, because I think one learns many things from it. Okay. Now, what is this uniqueness of complete reduction? The idea is the following. We have, as usual, these three things: a group, a vector space, and a representation of the group on that vector space. Suppose we assume, we will assume, that this representation is fully reducible. That is, it can be written as a direct sum of irreducible representations. That's the meaning of full reducible. That means fully decomposable, no off-diagonal blocks ever surviving. Now, so we are assuming it's fully reducible. So, this representation is given to two of you. One of you, both of you are told, go forth and reduce. All right. So, you take it representation and you reduce it fully into irreducible pieces. He takes it, he also does it separately without looking at your calculation. Will you get the same result or will you get different results? When you compare the complete reduction into irreducible pieces, will the answers look the same? To what extent will they look the same? In what way can they look different? Schur's lemma gives the answer. Certain aspects or properties of the reduction will be the same, certain things alone can differ. So, what we are imagining is that the reduction is carried out by two gentlemen, ladies, two gentlemen, doesn't matter. How much is common and how much can be different. So, I will use the following notation. I will write one reduction into irreducible representations in this way. I will say that the L1, L2, etc. are subspaces of the vector space. They are mutually disjoint. They don't have any vectors other than 0 in common. Their direct sum gives you the full vector space. And when the given representation is made to act on each of these subspaces, we will imagine that on the subspace L rho, a certain irreducible representation of G appears, which I will label by rho. And now, another person solves the same problem. He finds he is able to decompose the full vector space into a series of subspaces M1, M2, M3, etc. And he finds, he shows that in the sigma-th subspace in his reduction, the group acts irreducibly, and let's suppose that we give it the name d sigma. So this is equation 48 in my notes. Now what can we say on the basis of Schur's lemma? Can these be completely unrelated, or are there some things which are shared by these two decompositions? So here is what you do. You start with a vector x rho which lies in one of these subspaces in the first decomposition into irreducible representations and irreducible subspaces. Now, any such vector can be analyzed from this point of view. Any vector in one of these L rows, certainly it can be written in a unique way as a linear combination or a sum of vectors belonging to these subspaces. That's the meaning of V being this direct sum. So I should be able to write this as a sum of contributions from the M subspaces looking like this. So given an X row, the components Y sigma must be uniquely determined because it's a direct sum decomposition into subspaces. All right. So we are taking vectors in one of these at a time, breaking it up into pieces in these subspaces. Now let us apply the representation D, the group action, to both sides of this equation. And I will just write the various steps and you will understand what is going on. This is clear because I start with a vector in the invariant subspace L rho. I know that in that subspace the group acts through an irreducible representation D rho. So this must be true. No summation over the repeated index here. I now go back to the other way of viewing X rho as a sum of contributions from various M's. I take the D inside the sum, and what does it say? Each Y sigma is in an M sigma, and in M sigma we know the group acts by the sigma-th irreducible representation, so this must be true. Okay. Now I go back here and define a linear operator T sigma rho from each L to each M by the rule it picks out the component of X rho in M sigma. I think I have missed some equation. Sorry, this is 50. So I have introduced a linear mapping T sigma rho, which takes a vector in L rho and tells you what does it contain from M sigma. So that is that definition. Right. Remember, X rho is a sum of various Y sigmas from various M sigmas. So T rho sigma rho is an operator, it picks up one term in this summation. Now I leave it as a simple exercise for you to put all this together and derive the following derive this equation. Just there is no summation on any index here, even though they are repeated. If you spend just half a minute, you will see that this is what one can read off from the previous equation. What it says is that this T operators which map vectors in L rho to M sigma in a linear fashion, they intertwine these two representations. The one that is acting on L rho, the irreducible representation, the one acting on M sigma. So we have produced an operator, a set of operators T sigma rho for each choice of sigma and each choice of rho, which intertwine the respective representations. So what I will do now is rub out the X rho because it is true for all X rho. So I have produced a situation where we can apply Schur's lemma. So what are the conclusions that we can draw? So we say for each pair sigma and rho, there is a corresponding linear operator T sigma rho carrying vectors in L rho in one decomposition, subspace in one decomposition into subspaces in the other decomposition. We see that this must necessarily be 0 if d rho is not equivalent to d sigma. Correct? That's from Schur's lemma. This is a symbol. A tilde sign means equivalent representations, and this is non-equivalent. So when you compare this decomposition into irreducible representations with this decomposition into irreducibles, vectors in the first decomposition, when analyzed in the second decomposition, they can have components only in those subspaces here where the irreducible representation is the same as the one on the left. All right. So just for argument's sake, suppose there is one piece here which is a 3-dimensional representation, one piece here which is a 7-dimensional representation. And X in this 3-dimensional subspace can have no component in that 7-dimensional thing. It's just one illustration. More generally, if d sigma and d rho are inequivalent, there can be nothing non-trivial connecting the two subspaces. But then you argue, next step, this is the first conclusion. This can be non-zero only when it connects subspaces on the left and on the right carrying equivalent representations. Only then T can be non-zero. And when it is non-zero, of course, it is non-singular by Schur's lemma. Yes, vector in one of the L subspaces has components only in those M subspaces which carry the same representation as that L. And the argument can be reversed also, because everything is symmetrical. All right. Now, supposing you take X rho in L rho and you expand it in the M description, at least something must be non-zero here. If X rho is non-zero, at least some terms here must be non-zero. It can't be that everything is 0. What does it mean? If a certain irreducible representation of G is found in this reduction, it must be found somewhere in that reduction, and vice versa. Correct? Because otherwise you will find that there is a subspace L rho carrying a representation irreducible d rho, and if it were the case that no d sigma is equivalent to d rho, all the y's would have been 0. But how can that be? Because we know X is non-zero. So every irreducible representation occurring here must also occur here, and vice versa. So you see already that there is certain degree of uniqueness in the reduction contents of the reduction process. But that is not all. One cannot say that one can go as far as setting up a one-to-one relationship between the L's and the M's. It need not happen that every L is some M. That need not happen. What we now do is the following. We introduce the following refinement of this notation. I say label the various inequivalent irreducible representations of G by a Greek letter alpha or beta and so on, to be distinguished from rho, sigma, lambda, the later part of the alphabet. Now, so a given irreducible representation, the alpha-th irreducible representation, may have occurred here several times. That is called multiplicity. So what we say is that let's suppose that the alpha irreducible representation appears 3 times or 4 times or some number, we will introduce a second index to count this multiplicity. So we will refine the notation and write it like this. The index rho will now stand for a pair of indices, alpha which tells you which irreducible representation, k which tells you is it the first appearance, the second appearance in the sense of a direct sum, and sigma k what j k l, I don't know what j. All right. So these Latin indices all right. So we will refine the notation. I'm sorry, I have interchanged k and j here. Please don't mind. So with this double index notation, each L carries or supports this irreducible representation of the group, and this second index tells you how many times is that representation occurring. So now what are we able to say? I will now try to speed up. These intertwining operators vanish if the two representations are not equivalent. Alpha labels an irreducible representation up to equivalence. Beta represents also. So alpha not equal to beta means inequivalent representations. Then what we do is we collect all those subspaces carrying the same representation, put them all together, call it L alpha. Here, take all the subspaces carrying the same representation and call it M beta. All right? So now you can see very quickly, if I start with any vector in the vector space in this subspace, so this is a coarser breakup into subspaces. You are collecting all the L's which carry the same representation again and again. Put them all together, make a larger subspace. Any vector in an L alpha can only have y components in M alpha, not in an N beta for beta different from alpha. Similarly, any vector in M beta can have only components in L beta. What does it mean? L alpha equals M alpha. Any vector in this is in that, any vector in that is in this. So this is the conclusion. This is the uniqueness of complete reduction. In case the representation was what is called simply reducible, that means it can be reduced into irreducible representations, and if any irreducible representation occurs, it occurs only once. Suppose that was the case. Wigner has given this name simply reducible. SR is the notation used for it. In that case, each of these supports some irreducible representation, different ones support inequivalent ones. This will also be true here. So in the simply reducible case only, each L is equal to some M and vice versa. The two decompositions themselves coincide. But if there are multiplicities, to what extent does your result agree with your friend's result? Not at the level of individual subspaces L and M, but at a higher level, at the level where you collect together all occurrences of a certain irreducible representation here or there. They will be the same, but not the further breakup into resolving the multiplicity. because resolving the multiplicity is a choice in your hands. The group representation doesn't tell you how to do it. It cannot tell you how to do it. If the same representation occurs 2 times, how you are going to separate them is completely arbitrary. There's a lot of flexibility. So this is the extent to which there is a uniqueness, commonness in the 2 reductions of a given group representation. It's a very nice result, and it says that summing up over the multiplicity of each irreducible representation, the 2 decompositions have to be the same. They cannot differ from each other. Okay. The further reduction of each L alpha into subspaces alpha j for various j, counting the multiplicity, that is completely arbitrary. You may get one result, your friend may get a different result.
When
Yeah.
you say simpler and simpler level,
Yeah.
almost remains what now the
Yeah.
spectral resolution of a efficient operator will regenerate like that.
Yeah, exactly. Exactly. That can also be put in the language of group representation. You take one Hermitian operator, its exponential defines a U1 group. And this essentially does that. Exactly. Does everybody understand that? Everybody understand what he said? Okay. So then I start just the beginning of the next major application of the Schur lemma, and it will be carried forward tomorrow, but I'll just set up the basic notation. So this topic is a topic of the orthogonality relations. So since it is close to 6:15, I cannot complete it today, but I will just start. What this application of Schur's lemma leads to, it shows you the most important properties of the matrix elements of irreducible representations. Matrix elements are always defined once a basis is chosen. So these are consequences of irreducibility of group representations derived from Schur's lemma, consequences for matrix elements of irreducible representation matrices. So it's a very nice tool which we have to introduce for this purpose. So what I will do now is introduce the gadget that we are going to use, and we continue tomorrow. Suppose you consider a function on a group, and let us imagine, just to begin with, that it's a complex valued function. Could have been a real valued function also. Let us take it to be a complex valued function. So for each group element, the function f at the group element G has some complex number as its value. In the differential geometry, people introduce a certain kind of notation which is very suggestive. This set of functions on an object, on a set, obeying various conditions which you may impose, is denoted by script f. This is a nice notation in differential geometry jargon. Script f means function, and so little f is some function on the group. Given such any function, we can think of it as belonging to a complex vector space of dimension equal to the order of G, because how many components does it have? As many as there are group elements. So a complex valued function on a group can be thought of as a vector lying in a complex linear vector space whose dimension equals the order of the group. Very simple. For any such function, we can define formally something which we call the mean value of the function. And sometimes I will write it, it is useful to write it in a somewhat more explicit fashion. The mean value or the average value of the function taken over the group, the element of which is G. So for the case of finite groups, we define it in this way. So now I began by imagining that the function f we are talking about is a complex valued function. It means for each given argument g, f of g is a complex number. But you can see that this expression, the idea of the mean value or averaging over the group, it has perfectly good meaning for a wider choice of f. What is the basic requirement you must put on f in order that this be meaningful? It must be meaningful to add. So what do you require of f? It must belong to a linear space. That is all. So f can be not so represented as a complex valued function, but it could belong to some linear space. So for each group element, f of g is an element in that linear space, a vector in that vector space. So it is quite flexible in that sense. Now, the main properties of this definition, oh, by the way, this is for the case of a finite group of finite order, just a point by point averaging. And that's why by normalization I divided by the number of terms. If one had a compact group in mind, like the rotation group, which we will study in great detail in the next section in this course, we will have a formula generalizing this. It will involve integration. When we come to it, you will recognize it is this generalized to the continuous case. Now, this has the following basic properties. It is linear. The average or the mean of f1 plus f2 is the mean of f1 plus the mean of f2. If lambda is a scalar, let us say a complex number, lambda just comes out of the mean value. Suppose f was real, non-negative, the mean value is non-negative. Just the idea that there are no minus signs here. This is adding, every term comes with a plus sign. And if I take the constant function, f equal to 1 at each group element, what is its mean value? 1, because I have normalized it by the order of the group in the front. And the last set of conditions, and for this I use this more detailed notation. Whether you take a function f and average it, or you take f of g inverse, will you get anything different? If you average f of g inverse, think of f of g inverse as a new function. F prime of g is the value of f at the inverse element. Will it have the same mean or not? Why? Every element has a unique inverse. Every element has an inverse, it is unique. So whether you run over the inverses of all the elements or run over all the elements, you're running over the same set. No repetition, nothing. Will this look any different for fixed G0? No. What are we using here? the possibility of cancellation. And what else can I write? So this mean value operation, because it gives equal weight to every group element in the finite case, discrete case, it is inversion invariant, it is left translation invariant, and it is right translation invariant for any fixed G0 in the group. Okay. So I'll just give the equation number for this. Now what we will do tomorrow is combine this idea of the mean value of a quantity belonging to a linear space, combine it with Schur's lemma, and then get the great orthogonal relations. So I think I will stop here. Very good. Thanks.